He will not force.
Good morning. How many of you here are astronomers? Astronomers don't do 9 a.m.s. That's why there's so few astronomers here. Okay, so my name is Mario Juric. I'm at the University of Washington, and in LSST, I am responsible for leading the team that's building the data processing system. So I'm going to be talking today a little bit about what LSST is going to deliver, also how to think about it. Many of you are new to LSST, to the Dark Energy Science Collaboration, to this school. So we thought that it would be a good idea to kind of go through the basics of what it is we're going to deliver and make sure we're all on top of that. This is usually the slide that I show last. I wanted to make sure that you see it, so I'm showing it first. This is where you can find out more about everything that I'm going to be talking about. These 3 papers and these 2 websites are places that are a good jumping off point for anything LSST data related. Okay, so when Pat asked me to give this talk, she said, make sure the audience is engaged, that it's active learning, that it's all great and cool. And I said, yes, maximum effort, I'm going to do it. So I had everything planned out. I was going to do a Star Wars theme thing. We're going to have Imperial Troopers. We're going to have Boof Jane and Imperial Regalia come here and try to convert a solar system postdoc to do dark energy. We're going to have Jim Bosch, one of our DM shape measurement experts, going to be Han Solo. We're going to, Robert was going to come to him, dressed as Jabba the Hutt, look at his coat, and say, Jimma buke kelekaya duka. All right, so look it up, see what it means. Then I realized I have an hour, so all of that went away. So instead, we're going to do polls. It's going to be awesome. I will occasionally be asking you questions and asking you about your opinion on things. And the way we're going to respond in real time is by going through this website. Pick any device that's internet connected, go to this website, and you should start seeing questions and answers. And the cute thing about this is that, assuming it works, and it better work because I gave him $100 for this, we will see the results in real time here online. And also, for a number of these questions, I'm going to ask you to discuss them first, to discuss the question with your partner before answering. So let's try this out. So here's the first question. So you should see it. All right, try to answer this. All right, so time's up. Let's see the results. And there we go. Empire Strikes Back is the best. Really? Really, people? No, it's anonymous. All right. Now let's do something a little bit more serious. So let's get to know each other. So just type in your first name. There are many people named Chris and David.
Come on, Chris. I love this presentation.
Ooh. All right, here's the distribution of names on the 2016 Dark Energy Summer School. And I'm going to cut it off in about 10 seconds. So you have 5 more seconds to type in your name. And after that, it's committed to history. David and Andrew, interesting. Okay, thank you, everyone. Another one. What's the stage of your career? And now we're getting to more serious questions because these will actually let us tailor the school a little bit better to the audience. So let me give you a couple more seconds. Wow, you're fast. There's already 54 people who have responded. So if I unblind the results, wow, we have no high school students. You never know. Okay, so thank you for that. I think now you know how this works. I know that it works. Whew. If it didn't, this would have been a disaster. And two more questions for starters. And these are less about actually this talk, but more about future talks today and future lessons. So which version of Python you're most comfortable with? Is it 2.7, is it 3x, or is learning Python still on your to-do list? It's a type of snake common in the Everglades, apparently.
So Mario, is GM going to switch? Is GM using 3, Python 3, or going to switch to it?
We're using 2.7 right now and switching to Python 3 compatible code, so it's going to be able to run on both. Okay, here we go. So, so right now it seems like most people are using Python, or most comfortable with Python 2.7, and there's a fraction who are most comfortable with 2.3, and a number of people who are still working on learning Python. And this is the final one for the start. How do you get your Python? Do you buy it in a pet shop? Do you use the default that comes with your OS? Do you use Anaconda, Enthought, or Homebrew or Thinkum, or other similar packaging systems for the Mac? And the reason why I'm asking this question is it's going to help us actually make it easier for you to install the code if we know what is it that people are actually using. Okay, so if I unblind that, Anaconda seems to be quite popular, 56%. A lot of people are using whatever comes with the OS, and then there's a number of people who are using Mac ports, Homebrew, etc. Apparently nobody has a Python pet at home. All right, such a conventional crowd here. Okay, all right, enough with the fun. Thank you very much for answering these surveys. These are actually going to be useful for us going forward. So let me now start with my talk. I'm going to be talking about what LSST is going to deliver, but I'm also going to tell you a little bit about the context on how you should think about what LSST is going to be delivering. And this is going to be a little bit broader than just dark energy. My background is not primarily in dark energy. My background is in galactic structure, solar system before that, and so forth. But as you'll see, LSST as a survey is very, very versatile survey. And one of the things it's going to allow us is by creating a very versatile data set to solve multiple questions and multiple problems, dark energy being one of them. So when you think about LSST, I don't want you just to think about dark energy. I want you to think about the whole, the entirety of the ability of what LSST is going to enable, and then you can focus on dark energy. So let's talk about large surveys first. Astronomy has actually started with surveys, and quite some time ago. If you go back 2,000 years, go back to ancient Greece, you'll find a story of this gentleman, Hipparchus of Rhodes, who was brilliant at his time. Some of the things he did, we learn about today. He discovered the precession of the equinoxes. He measured the length of the year to 6 minutes. This was ancient Greece. This was before we had stopwatches. And the reason why I mention him here is that in 129 BC, he constructed one of the first star catalogs containing about 850 stars. So this was the large-scale survey of the day, the Hipparchus catalog. He wasn't perfect. He's also the one to blame for the magnitude system that we're still stuck with today. But I think everything else he's done redeems him in that sense. Now, astronomy was more or less observing the sky by eye, counting up the stars, measuring their positions, measuring how they move, looking at the planets, for the next 1600 years, until this gentleman came along. Galileo researched a variety of topics. He was a physicist. His discoveries are all over the place in physics and astrophysics. But here, he is of interest to us because of the introduction of the Galilean telescope. Now, most people think that Galileo was the one who invented the telescope. He didn't. Telescopes were known for a while in his time. But interestingly enough, he was the first one who did this, pointed it up to the sky. Probably he was not the first one to do that. Probably he was the first one to publish what he saw. Point being here, publish. Galileo's telescope allowed us for the first time to zoom in on the cosmos and to study the individual objects in great detail. And so you know that he discovered Galilean satellites around Jupiter, many other things, and so forth. So now we could do surveys on a grander scale and then zoom in on objects. That remained state of the art for another couple hundred years until Fraunhofer showed up. He mounted a prism in front of an objective of a small telescope and pointed it to the sun. What did he see? Yes? Lines. Yes, and what were those lines? Absorption lines. And what was the most interesting absorption line there that no one ever saw on Earth? There we go. Just be louder. You know this stuff. This is physics. Fraunhofer began the birth of modern astrophysics. Now we were in the era where we were not just looking at the sky and cataloging what we see. Now we're in the era where we can actually tell what's physically going on there. And this kind of became the standard for astrophysics. You would do a survey, you would construct a catalog, construct maps of objects in the sky, focus on coarse classifications of those objects and discover targets for further follow-up, and then do the Galileo/Fraunhofer thing, build a larger telescope, acquire detailed observations of few representative objects, understand the details of astrophysical processes that govern them, and then extrapolate that to the entire class. So this was how we started discovery, this was how discovery ended. And when I give this talk to kind of more broader audiences, I show them an analogy with web search. So if I go to Google, Google's index, in effect, is a catalog of the web. We use it to locate objects that are consistent with some requested classification. In this case, I asked for what is two-step. And then you can use it to zoom in on individual entries to find out more by clicking on the links. So if you type in two-step, you will find the first link is a link to Wikipedia. Apparently, two-step is a dance move popular in Texas, of all places. And if you click on the second link, you will find this gentleman on YouTube who is apparently really good at it. 800,000 views. Mm-hmm. Now, this is astronomy. We have a survey, gives us a catalog, gives us coarse classification. We then go and zoom in with bigger telescopes. However, a funny thing started happening with Google a couple of years ago, now almost a decade actually, where if you start typing in questions that are more complicated into Google, so let's say I say weather Oxford, UK, it will give me not just a link to where I can go and look up the weather, it will actually give me the weather forecast for Oxford, UK. So what's happened over time is as Google's index grew, it became more than just a catalog of pointers because it encompassed most of the web. It not just only collected links to websites that are attached to keywords, it understood the details. The information got much more richer. So more and more, Google itself collects, processes, indexes, visualizes, and serves the actual information that we need to complete our research. So more and more often, there's enough information in this catalog that we don't need to go and do that final step of zooming in into a particular object. And what's standing between us and that information is the ability to mine it. And that's what Google did with building all this software on top of their search data set. So what I'm going to be arguing is that in astronomical surveys, we are entering an era of massive sky surveys, and it's somewhat analogous to this. There's a close parallel in scale, quality, and richness with what I just showed you with what happened with web searches. So in terms of scale, we're entering into the era where we can image and catalog more or less the entire sky. You know, half of the sky is the entire sky to within a factor of 2. We're astronomers, so we're okay with that. In terms of quality, the measurements can be as precise now as those taken with pointed observations. It used to be that when we did surveys, for example, photometric accuracy was 5 to 10 times less than what you could do, or worse than what you could do when you did careful pointed observations, taking your calibration stars and so on. And in terms of richness, now these catalogs contain not only positions and magnitudes, but also shapes, profiles, and temporal behavior of objects. So you're collecting much, much, much more than you used to before in these catalogs. They're not small and boring anymore. Quite often, they have enough information for your research to begin and end with the survey. That hasn't been the case forever in astronomy. And I think that this is what makes large surveys today not just bigger, but better, more information-rich, and therefore different. It's not the size here. Yes, we can now observe the entire sky, which is great. So size is part of the answer. But it's not just that we can observe this many objects. It's that we can actually find out so many different details about those objects, and that we can store all of that, and that we can then try to draw connections and try to draw inferences from the behavior of those objects in time, behavior of those objects in space, et cetera, et cetera, et cetera. So this big data in astronomy really is less about how many petabytes you have. It's more about complexity and optimal knowledge extraction. How do you extract information about the piece of science that you care about from that data set, not the size of the data set itself. And so we're now shifting in an era where a lot of the data that's already in the surveys is sufficient for us to do a lot of the research. And we actually have been in that era for a while now. So I think the first survey that really brought this to bear was the Sloan Digital Sky Survey. I think a number of people in this room have worked on it. In about 10 years, Sloan collected on order of 10 terabytes of imaging data, imaged about 14,000 square degrees of the sky, 5 bands, 2% photometry for more than 500 million objects. And this has been improving over time with constant reprocessing. Fast forward about 10 years and you have Pan-STARRS. Pan-STARRS is about to become public in about 2 months, or so they say. Pan-STARRS has been generating 700 gigabytes per night, and it's been operating for about 3 or 4 years. And if you fast forward another 5 years, we are going to have LSST on the sky. And LSST will be imaging roughly half of the sky. It's an 8.4 meter telescope, 10 millisecond astrometry, systematic limited. It's going to be generating on order of 15 terabytes of imaging per night, high quality imaging. That's about 5 petabytes per year. And that will generate a catalog of an order of 20 billion galaxies and 20 billion stars. So this is the survey that we're going to be talking about this week, and that you are going to be using to do your science. Let me tell you a little bit about the status, where LSST is now. We are building it in Chile, near La Serena, on a summit called Cerro Pachón, summit called El Peñón in Cerro Pachón. This was the image a couple of years ago when the top of the mountain was blown off to make room for the telescope. This was an image about a year ago when the first stone was laid. And this is an image as of yesterday. So this is what LSST construction site looks like as of yesterday. This here is the mountaintop. You can already see 2 stories of the support building and the pier of the telescope. This is the same thing, just image from the pier. You can see those 2 stories going up. And then this is the pier itself. In only about 2 years, the summit is going to look like this, plus or minus a panel here and there. The point of this is that we are almost halfway there to getting the building done. So this telescope is becoming real very fast. The mirror is already completed, the primary and tertiary. It's being shipped to Chile. This here is the cell that is going to be holding the mirror while it's in the telescope and also while it's removed from the telescope. It is also in the process of being constructed. This is a big chunk of metal. Remember, the mirror is 8 meters, 8.4 meters in diameter. The camera, which will still be the largest optical astronomical camera when it's built, is in the process of being constructed. I don't have a more recent image of what the camera, what the chips look like than this one. This is years old, and these are actual engineering samples. But in the camera, we've received about 10 science-grade sensors that are in the process of being tested. We have to receive another 170 at least. So there's still a long way to go, but these will now be coming in roughly at a rate of 1 per week for the next 3 or 4 years. And so this whole telescope is being put together. The final piece of that puzzle is the data processing system. And the data processing system will take all the data that we collect on Serapachan, and we'll send it through high-speed network links up to the National Center for Supercomputing Applications in Urbana-Champaign. We're going to have our primary processing center at NCSA. We're going to be sending a copy to Lyon, France, to CCI and 2P3. So there'll be a copy in the US, there'll be a copy here in Europe. Lyon will be doing half of data release processing, NCSA will be doing half of the data release processing, and the 2 will be exchanged every time we need to do, the 2 halves will be copied from one side to the other every time we need to do a data release. And then there will be a data access center here in Lyon and another one, in Lyon and another one at NCSA. And from what I understand, there's also preparations to have one in the UK as well. So this piece here is also being constructed. These networks, thankfully we're not building them, we are leasing them. And we've signed the contracts for a lot of these. So all of this is getting prepared, and it's getting closer and closer to actually being done. So what will we actually deliver? So we will have that telescope on the summit. The telescope will be observing every night. The telescope will be collecting those images. As they come in, it'll be sending them up to NCSA. And then what? Then we do some data processing. When we do some data processing, we create something, and then we offer that to the users. So now this is a time when you wake up, because I will ask you to think a little bit about what you know about LSST, and try to think of one word that you feel describes what LSST will deliver, and talk to your partner about it as well. And I'm really interested in how this is going to turn out. And don't worry, there are no wrong answers on this one, because it's how people perceive this telescope that's actually going to tell us a lot on how we need to build it. Wow. Okay. So, let's see. Most people have said data. Anyone, can someone who said data, can you raise your hands? Anyone who said data? Okay, let me pick someone at random. Craig, what did you mean by that?
Well, I mean, that's ultimately what it's story.
That's true.
That's just a way to summarize that.
Anyone else? Let's see, cosmology, not surprising, given we're at the dark energy school. Science, this is interesting. So how is LSST going to deliver science? Who said science? Robert, how is LSST going to deliver science?
Well, not quite. It's closer to the data.
Somewhere in between?
Yeah.
Okay. Catalogs, astronomy, huge. That's a popular word in the US these days. Okay, so here's my answer. This is how I think of LSST, and now you can understand my biases occasionally. My answer is database. My answers are also depending on the day, data set, catalog, and so on. But when I think of LSST, I don't think of the telescope. I don't think of the camera. I don't even necessarily know that those exist. But when I think of LSST as the user, I'm thinking of the database. That's where my science is going to be coming from. That's our primary data product. So the way I think of LSST is that its primary deliverable is not the telescope, nor the instruments, nor raw data. From the point of view of us here in the room when we put our science hat on, it's the fully reduced data products. It's a facility that delivers data products and data access and analysis services so that we can all take them and go and do science. And our primary challenge within the LSST project, the challenge of the data management subsystem, is how do we create useful general purpose data products while minimizing information loss? I'm going to tell you about that, something about that in a second. So we want to give you something more than just raw data, but we don't want to ruin it in the process. How do we go from data to knowledge? We do it by inferring something about the world that we're looking at, by having some model, inferring something about that model through this inference, through an inference process that kind of roughly schematically could be described as going like this. You can imagine this as being just Bayesian inference. What is data? Data is literally what the telescope collected. So that is the only unchangeable thing that the LSST will ever produce. Once we download that data from the camera, once we store those pixels, that raw data, we can burn it onto DVDs. That will never change. Everything else that's touched by software is subject to change. So we as scientists take data and metadata. By metadata, I mean, what were the conditions in which these images were taken? When were they taken? What was the temperature of the mirrors? What was happening outside? We run them through some inference process that is computationally expensive and cognitively as well, because let's imagine, this is easy to understand if you come up with a concrete problem. Let's say you want to understand how many stars there are in a particular part of the sky or in the galaxy. If all you have are the images, what you would do is you would need to infer something about the number of stars by writing the software to detect where the stars on the images are by counting them up. Another possible way you can do it instead of writing a software was getting a graduate student who's going to be extremely unhappy by your choice of a project, counting up stars and images, namely. And by the way, this is how this was done 20 years ago. So this is what I mean by cognitively expensive, because you need to write a lot of code that has to do with image processing and understanding the instrument to go from how many from the data that are actually images of the sky to your model, which is how many stars are there, what is the distribution of stars in a galaxy, and so forth. So to not do that, virtually for every survey, we expand this inference process. We break down this inference process into a little bit longer chain. We still start from data, but then we do some data processing that generates catalogs. And then catalogs are the things that most of us start with to do inference, to learn something about the physics and about the astrophysics. The challenge in generating those catalogs, or the challenge now, the inference challenge, has largely been shifted to data processing rather than the inference part. The data processing bit is now that's computationally expensive, but it's general. So I can once and for all find all the stars and galaxies on images, assess whether they're stars or galaxies, measure their positions, measure their shapes, store that into catalogs. The way to think about that, the way to think about going from data, which in our case are images, to catalogs, is you should think of that as, it used to be that that was a compression step. So you would take one big image, and instead of one image to describe everything that's interesting on the sky, you would now find locations of objects and maybe measure the magnitudes and write it all down. That was a much shorter description of what's on the sky. These days, we're measuring so many things about these objects that I started thinking about that as reprojection. So instead of describing what's happening on the sky in pixel space, where it tells you at this location of the sky, here is the surface brightness. This location of the sky, here is the surface brightness. That's what your pixels are more or less telling you. You are now reprojecting those pixels into something that's much more closer to the physics you're trying to study, into the catalog. But each row in the catalog that describes one object may actually have more numbers, more features measured than there are pixels in that object. So this is not compression anymore. Now it's a reprojection. But now in this catalog space, you will know you will have a much better idea of what to do next to derive your science, rather than having to go yourself to this data processing step. This almost always introduces some information loss, because we have to assume something about the objects that are out there. Take, for example, the blending. So every single object beyond some magnitude, so when you go down 26th, 27th magnitude, I don't know who came up with this, but I'm going to say Robert, because he comes up with everything. There's no such thing as an isolated galaxy. There's no such thing as an isolated object. They're all blended together. How do you split them apart? This question actually involves, the answer to this question actually involves putting in lots of priors, lots of assumptions about what you believe galaxies look like, how you believe they should be deblended. And that almost always introduces some information loss. And then when I say here, this is almost a footnote, when I say data processing, this also includes instrumental calibration and measurement of those objects. But now, once you've done that, then inference from the catalog becomes much more computationally cheaper. You don't have to reprocess every data set. It becomes easier to understand. You don't have to understand the vagaries of brighter, fatter effects in LSST detectors to measure shapes of, or to study, to build cosmic shear maps if the catalog has been done right. And it's now, this is where you put science case specific stuff. So not here in data processing, but here. And so this is where we as LSST, what the LSST project is trying to do. On your traditional facility, you go to the mountain, you take your data, they give you the images. You go home with the images and then you try to process them and do your best. With surveys, just because there's no way everybody's going to do this all by themselves, and also because the kinds of questions that we're trying to ask require the knowledge of so many different things about the telescope itself. In surveys, the facility does this for you. And now, the challenge is, as I said, this is a reprojection. It introduces some information loss. So this is not going to work for everything. And the challenge for us is, how do we pick things that we're going to measure and then we're going to put into catalogs? There's virtually infinite numbers of options of what quantities one can measure, But if we think of this as a, what's called a generalized cost reduction tool, then the guiding principle becomes easier to define. And when we in LSST think about this, we think about the following three things. One, we try to maximize the science enabled by the catalogs. So we're trying to build catalogs that respond to most of our science cases. Working with images, as I said, takes time and resources. A large fraction of our science cases shouldn't require images. And secondly, there's going to be a huge dynamic range of science possible with LSST. Some of it will require very careful measurement, where some of the things you measure in non-traditional ways. For example, instead of just having a maximum likelihood estimate of a galaxy's flux, you may want to know the full posterior distribution, full likelihood function. But perhaps 90% of the users won't actually care about that. So one of the things that we're trying to do is be considerate to the user and provide even such, let's call them suboptimal measurements, if they will enable leveraging of existing experience and tools so that you don't have to relearn everything you've known, even if it's slightly suboptimal, that you can learn as you go. The second thing we try to do is to minimize information loss, so provide as much as possible in the catalogs. So that includes estimates of likelihood surfaces, not just single point estimators. So that's going to become very important for cosmic shear estimation. And finally, we provide and document the transformation. I call this the transformation, going from pixel space to catalog space. That transformation is the software. So today, if you wanted to, for example, pick up SDSS software and rerun it on SDSS data to reproduce the catalog or to modify it slightly to reproduce the catalog, that's actually not that trivial. And I'm being generous here. With LSST, is one of our requirements is that we want to make it fairly straightforward to do that, so that you understand what's happened going from pixels to catalogs. How do we, given these principles, how do we choose? Well, what are the discoveries that we need to enable? This here is a dark energy school, but there are actually four main areas that LSST is supposed to enable. One is the time domain science. So we want to know how objects change through time. We want to detect thousands or hundreds of thousands of novae, supernovae, GRBs. We want to characterize those sources. We want to know instantaneously when some of those have happened. We want to do a census of the solar system. We want to find all the asteroids, make sure we get them before they get us. We want to map the Milky Way. This here is actually real data from SDSS, and these circles are where LSST may be able to take us. And also we want to enable the understanding or constraining of the nature of dark energy. So we take the three principles that I just mentioned, and we discover that roughly this is what we need to build or to deliver for LSST to be a success. I call this a data stream. That is level one, a stream of about 10 million time domain events every night. So as imaging comes in, we transmit alerts that new things have appeared in the sky or that things have moved. So that's a data stream. A database, that's a catalog that's going to grow to about 40 billion objects after 10 years, 7 trillion single epoch detections, and roughly 30 trillion force sources. We'll be producing this annually. We'll make it accessible through online databases and make deep co-added images accessible with it. And then finally, I've been thinking a while how to describe this third part, that I decided I'm just going to call it a small cloud. So we are going to also enable or put together services and computing resources at our data access centers to enable user-specified custom processing and analysis next to the data. So if you have some computing where you don't want to necessarily download hundreds of gigabytes or hundreds of terabytes of data, you want to do it at the data center, that's what level 3 is supposed to enable, as well as giving you software and APIs to make it easier to enable development analysis code. So I'm going to delve a little bit deeper into every one of these, into these three levels. Level 1 is about enabling discovery and rapid follow-up of time domain events. So this is if you care about knowing something at a time scale of a minute to a day or a couple of days. This is if you care about chasing GRBs, if you care about chasing supernovae, if you care about discovering rare objects in the universe, if you care about finding asteroids. We will do real-time image differencing as observing unfolds each night. We will perform detections on those image differences. We'll measure on the image differences. We'll associate with pre-existing observations that have been stored in a database. And then every source that we detect that way, for every source that we detect that way, we'll emit what we call an event alert. And all this will happen within 60 seconds of observations. So if you care to know, for example, about fast-moving asteroids, just out of curiosity, does anyone here care about fast-moving asteroids? I thought it would be awesome if that Venn diagram resulted in an overlap. It would be amazing of dark energy and the solar system science. If you want to do those kinds of things, then this will enable that. Who here cares about supernovae? There we go. Supernovae, finding interesting supernovae, will be enabled by this data product, by this stream that will be going out, and it will tell you something exploded or something new appeared here. It's close to a galaxy. A few observations later, you may know its light curve. You may decide you want to go follow it up, and so on. The primary use case here is to enable real-time recognition and follow-up of transients of special interest. And so the way that works is we're going to get these images in about 5 seconds after observation. We're going to start differencing, detecting, and measuring on them. 50 seconds later, so in 15 seconds after observation, all of those measurements will be done and committed to an internal data store. And then in 60 seconds, as I mentioned, alerts will go out. In about 24 hours, you'll be able to query all of these alerts. So these alerts are kind of, you can think of them as a stream. Think of it as an RSS feed, a very big RSS feed, Twitter feed. In 24 hours, you'll be able to query them from the database. In 24 hours, you'll be able to access the images on which they were detected as well. And then in 24 hours, you'll also be able to detect to access the newly discovered solar system objects in the solar system object catalog. So roughly, you can see that that this is all about speed, quickly finding what's changed, quickly alerting on what's changed. These alerts, when I say alerting, will include everything that we know about the object. So photometric, astrometric, and shape characterization, so where it was, how bright it was, whether it's a point source, whether it's actually consistent with something else. We'll include cutout images, so you can actually, in some cases, literally look at the objects. The time series of up to a year of all previous detection of this source. So if you've seen this source before, we will give you those time series in the alert packet. So you can immediately run your classifier and decide whether this is consistent with a class of object that you care about. And various summary statistics, so features computed on the time series. The most obvious one would be period. Yes, question?
Don't you have to do multiple differences between successive images and between stored images? How many differences?
So we do one difference for every image that comes in. And when I say the time series, that's because we store all those differences or the measurements, and we just cross-match positionally. So when a new object comes in, we check whether we've seen anything at that position. We associate that together, and that's what gets sent out here.
One difference you do is between successive images?
No, the one difference that we do is between the visit and between a deeper template that we built with previous imaging. There's an asterisk there because we actually, when we do snaps, so when we do each visit consists of two 15-second exposures. We actually treat that as one 30-second image for virtually all purposes, except that when we detect objects, we actually go back and difference the two 15-second images to just to verify that this object hasn't been changing at that time scale, at that short time scale. But it's almost an asterisk, a very powerful one. Yes?
When you say the time series, does that mean you plan to go back
No. So for this immediate alert, we don't do that. So we just look at whether it's been detected before. Actually, when we do data release processing every year, then we do that. We go and do force photometry. So, and in the meantime, there's also a service that if you see something interesting and say, I would really like to know what was happening in that area of the sky over the past 2 months, you can call into that service and say, please force photometry these images. And so that will be very interesting in areas where that can be a difference between doing follow-up and not doing follow-up.
Will LSST issue alerts after the first LSST visit based on previous surveys or only after the second visit?
After the second visit. Right now we have no plans to try to build templates, for example, using previous surveys. Would be a bit of a nightmare to try to, say, adjust for differences in band passes and so on.
All right, what's the hope for false positive rate?
Good question, and excellent phrasing. So the hope, what is the hope for our false positive rate? The hope is that we get it roughly to an order of 1 to 1. And that is quite an ambitious goal. But and this is after we apply machine learning to it. But what made us really happy was actually to see the results coming out of DES, where the false positive rates has been suppressed to even below that level with supernovae, yes. And so the hope is, that we will end up somewhere in that range. If it's 10 to 1, then it's going to be very difficult just because the size of the data stream is such that you cannot send it out. So we have to push it down. Yes.
Say something about the brokers and how individual meetings might try to get better.
So let me defer that to the end because I'm worried that will lead us into an open-ended discussion a little bit. But we're thinking about that. Let me make sure to ask me that at the end. I just want to make sure that I have a little bit more time left.
This feed is available to everybody that has no subdivisions.
Oh, I see what you're saying. So let me say a little bit about this. This feed, the feed that I talked about here, where I say we transmit everything we discover, we'll approach about 10 million observations per night. And that is way too big for any individual observer. So the way I think about it is we need to provide somehow, what we want to provide is a query service for that feed. Just like when you have a database, imagine SDSS. You have this wonderful catalog that has 1 billion sources in it. Typically, you don't care about the entire billion. You care about objects with within perhaps a certain RE-DEC range that you can observe, or objects with certain colors that you care about. That's why they're in the database. You can query them. We're going to provide a similar thing for the alert stream. So we'll provide what we call alert filtering service, where you will be able to select such subsets of alert candidates. And this service will let you create simple filters that limit which alerts are ultimately forwarded to you. So that means if you care about, let's say, R Lyrae stars, you may ask that only objects with a period of about a day that have a measured period with certain uncertainty of about a day be forwarded to you. If you care about microlensing events, you can construct a filter that will try to identify what a microlensing event looks like. And so these user-defined filters you'll be able to specify using an SQL-like language or short snippets of Python. And if you want to know what they look like, this is roughly in pseudocode what they might look. So imagine this as running a SQL query, except that now you can write this query in Python, which should give you even more expressive power in terms of what you write. We haven't actually written any of this code, so the details are subject to change. But this is an example of how you would find a never-before-seen event within 2 effective radii of a galaxy in Pythonish pseudocode. And I actually had here as a homework assignment, this was going to be the thing that we were going to try to work out here, but I'm afraid we're not going to have time. We have to compress a little bit these presentations. But I would ask everyone to try to think of and sketch out in Python-like pseudocode your own filter to select a class of objects of interest to you. And everything you need for that should be in the data products document. There we're describing how this service is going to look like. And then there's this link here that will take you to LSST baseline schema browser that will tell you what's going to be in the database, which fields. And so these are the sorts of things that we imagine doing for the level 1 stream. So you'll be able to write this piece of code, upload it through some, let's say, web interface or otherwise to LSST portal. And then when the night begins, your computer at the other end starts receiving alerts, only alerts that get flagged or that get allowed by this filter. So that's what we as LSST are going to be providing. So does that answer some of your questions? Okay. And then what I think Chris was also asking about is we're also going to have the capability to send the full data stream to what's called a community broker. If somebody else writes a facility like this, and potentially you can write a much more powerful facility that say, cross-correlates LSST observations with observations from other catalogs, from other wavelengths. Then we will be sending those kinds of facilities to those kinds of brokers, those kinds of software facilities. We'll be sending a full data stream, and then you'll be connecting to them and setting up these kinds of filters. But this is all still fairly in its infancy. The important thing is that there'll be ability to filter this stream. So if you're waiting there and waiting to do follow-up, you'll be writing filters, and your computer will be receiving alerts that get passed by those filters. David?
Are transients detected separately in each band? If one night is observed in R and the next night in I, would that be enough to, you need some sort of wavelength assumption?
We will be associating them independent of band. So if we have a detection in R at the same position where we had a detection in G the night before, we will assume that that's the same astrophysical phenomenon. So
if it didn't show up in a different filter, that would generate.
if it didn't show up in a different filter, that will generate a transient, yes, but we'll force photometer at that point. So you see it in G, we come back in R, there's nothing there, we force photometer. So, and send you the results.
Is there any thought or input into the system for extraordinary circumstances? Let's say I tell you there's a galactic supernova that's within neutrinos that happens once every 50 years.
Yes.
And it's happening at night. I'm telling you a few hours from now the optical light should show up. So is there a way to inject something into the system right now?
Yes, there are two facilities there. One are target of opportunity observations, so where you actually need to move the telescope to that part of the sky and observe. That kind of facility will exist. The other is that you can tell me, every time you're on this part of the sky, please force photometer this position, even if you don't detect anything. So we'll have the ability to do that. I don't know quantitatively how many. It's going to be impossible, of course, if we get 1 million positions from you and 1 million positions from everyone in this room. So there'll be some. Yeah. So, but there will be a facility for small number of such objects to be injected and photometered regularly. Okay. Okay, let me talk about level 2. What I talked about before was time domain. Level 2 is about enabling deep sky and high precision astrophysics. So I think this will be of of greatest interest to most people in this room. These are the catalogs that we produce annually. There will be well calibrated, consistently processed catalogs and images. They'll be made available in data releases. So it'll be every year except for year 1. With year 1 data, we'll build 2 data releases. We'll build one out of 6 months of data and one out of the first full year. The reason for that is just that even the first 6 months are going to be tremendously interesting, and we want to get that data out as soon as possible. For every data release, we reprocess everything. So these are not incremental data releases. In VR5, we don't just process what we've observed over the past year. We go back to the beginning and consistently reprocess everything from year 0 to year 5. And finally, our projected catalog sizes. In DR1, we already expect to see about 18 billion objects and 750 billion observations, and that will grow to about 40 billion, 37 billion in DR11, and 30 trillion in 30 trillion observations in DR11. So to me, this is interesting because this here is, or looks surprising at least in the beginning, because this here is after 6 months, this here is after 10 years, and the factor is only about 2. Let me give you a minute to talk to your neighbor about why there may be why there's only a factor of 2 and let's say not a factor of 10 in the numbers of objects. So why do we detect this many objects so quickly? And remember, this includes both galaxies and stars. All right, you have 1 minute. Go.
Due to that you have repeated surveys, so you actually come back and do the same object again and again, and that case you're not relating as a new one each time.
But every time I come back, I observe a greater or a larger chunk of the volume, right? So I would still expect that growth to continue. Yeah. Let's see if we have a few more proposals. Okay, Pat.
You think that after 1 year we're already seeing so deep that anything else we pick up after that is already blinded. And we didn't get it the first time. It's so faint that being blinded basically all the time.
So that's a very good point. But I did not take blending into account here. I would have to think about that. What blending is going to make this worse? But this was without taking blending into account. This is assuming perfectly blending.
Well, our second one is there's one here.
Okay. And one more. True. Okay. So I think Pat was the closest here. We're running out of objects. But interesting, which objects? We're running out of stars. Because we're seeing so deep, right? I mean, if you think of the universe, you can think of it, well, or you shouldn't think of it as homogeneous. I was going to say, you could think of it as homogeneous and it's going to go with some power law. But the galaxy, in the galaxy, we actually run out of stars fairly quickly. Even in the first year, we observe most of the stars we're going to see. And then in subsequent years, we push that, because the galaxy, the disk of the galaxy is actually fairly thin. We push that as we go deeper towards the galactic center. But there we have lots of dust between us and the galactic center. So it doesn't go as fast as you would imagine. So most of these objects here are going to be stars. So if you care about stars, you're going to jump on this data release, because there's going to be so many interesting things in there, especially when you cross-correlate with Gaia. And then we continue building up the object catalog from year to year, and the increase in galaxies is then much more pronounced. But you're the closest one. Yes, we run out of objects, but only a particular kind of objects. And this was interesting to me, but in essence, it basically says that the galaxy is finite, and the LSST is deep. Yes, question?
Will the mock data sets be provided in advance somehow, so before the first half-year data set, whatever?
Yeah, so we have mock data sets. Andy Connolly is our simulation lead for the LSST. He's also desk computing coordinator. He is the ruler of mock data sets. So he's the person to talk to. Not in my time. Andy's going to be here throughout the week, so he can give you much more detail. Okay, let me go on and let me tell you a little bit more about what's going to be in the catalogs, what's going to be measured. So in level 2 catalogs, for each object we detect, we're going to characterize it in several different ways. We're going to fit models to every detection. One model that we're going to fit is a moving point source model. That means, under the assumption that this object is a point source and that's moving, what is its position at some epoch? What is its velocity on the sky? What is its flux? That's what we're going to be fitting here. This is mostly of interest to folks who care about stars, because those are going to be the point source models, point source objects that are going to be best characterized by this measurement. If you care about shapes, then it's the double Juric model of the bulge splice disk that that's going to be most interested to you. So for this model, we will measure the maximum likelihood peak, but we'll also sample I say posterior, I should really say the likelihood surface for every object. So right now I'm being a little bit uncommittal here on how many samples from that posterior we're going to have. It's going to be on the order of hundreds, so about 200 independent samples. The people to talk to here are Jim Bosch, who I don't believe actually is here, and Robert Lupton, who's sitting up there. But this is the main product that we hope will enable the work of this collaboration. Now, in addition to these model-based characterizations, we're also going to do non-parametric characterizations, so centroids, adaptive moments, and ellipticity measures, aperture fluxes in Petrosian and Crone fluxes in radii per band, and we will also measure colors in a way that's seeing independent. We're also going to provide you with variability and statistics. So for each object, we're going to have on order of 800 to 1,000 observations at the end of the 10 years, and we will estimate period, lower order light curve moments, etc. So all of these are listed in one of the documents that I mentioned earlier. Yes, Pat?
Mario, when you say moving point source model, do you mean moving within the 15 or 30 seconds, or moving between
No,
visits?
I'm sorry, I should have said moving between visits. So think of this as a way to detect stars with high proper motion. And actually, in this point source model, you have to include parallax as well. So this will be really a precise way to measure, to do astrometric measurements. Okay, this is all I was going to say about level 2. And now I'm going to talk about a little bit about level 3 for the end. Level 3 is about enabling creation of added value data products, enabling analysis that you cannot do just by using level 1 data or level 2 data. So to start up this discussion, So let's think about, talk to your partner again, let's think about something that will be, given now that you know what's going to be in level 1 and level 2, that's going to be very difficult or impossible to do only with those data products. Something that will require you to go back to images or to do some... Oh, I'm sorry. All right, you can start talking, I will unlock it in the meantime. There we go. A few more. Chris?
Well, anything that relies on pixels and specifically calculating the system, either implementing or calculating the systematic errors in the algorithms where you have to go back to the images and figure if they change in some way, how would the output of the catalog change?
Okay, would you do that? All right, let me not, let's see. Mike?
Shear meta-calibration. Erikup's idea of reconvolving
Yes.
the shear.
Yes.
Joint modeling with LSST and space imaging.
Okay, Euclid or W first. Andy? Low surface brightness galaxies? We may actually detect many of those. You said low surface brightness galaxies. A few more? It's not a question over there. Can you speak more? Stellar mass function. Why would you not be able to do that from catalogs?
We play colors, we have to work out stellar masses.
Ah, I see. As a post-processing step on the catalogs. Yes, those are all good ideas. And so what this tells you is that LSST, and I apologize that this didn't work. That's because for some reason wireless stopped working, at least for me. That's one of the reasons why we're going to build this level 3 service. So to enable those kinds of science cases where you need to do more post-processing on the data than you would ordinarily, here we go. Okay. Okay, so I'm going to actually put this up. Yes, I'm done in two minutes. So I'm just going to put this up, and as I speak, you can still type this in, because then we will have actually a nice list of things that that one could do with level 3. Okay, so one of the things we're doing is we're developing a service that's going to enable you to do these kinds of computations. So that service is called Level 3. Level 3 is about enabling creation of these kinds of added value products. And here are my examples. So catalogs of supernovae light echoes. That's something that you won't be able to get out of catalogs, because those are big things that you discover when you difference images on long time scales. Characterization of diffuse structures, ISM. Extremely crowded field photometry is something that we don't guarantee we'll be able to do well. And then custom measurement algorithms. And so Chris mentioned, for example, strong lensing. We want to make these easy for the community to create and distribute, so we're going to enable this kind of analysis and processing at the LSST data center. Essentially what we're going to put together is a small Jupyter Hub cloud. So if you're not using IPython notebooks yet, start using them, because that's going to be a type of interface that you're going to have. And a small high-performance cluster resource. User databases and workspaces like you're used to with SDSS. And then the important thing, and this is where Robert comes in, is that we are going to make the LSST software stack. I still need that. You know,
I'm still leaving you
piece.
connected in. Only another minute.
We're going to make it available to end users. And so when I say we're going to make it available to end users, we actually already have. So if you're interested in running some of the LSST codes and you have patience to go through them, because they're not very well documented, then you can go to these websites, especially this one, pipelines.lsst.io, and see how to download and install it. And the latest release actually includes installable binaries. So with that, this is my summary. Wait. Of what LSST will deliver. So the things that I want you to take home from this is that the scale and precision of surveys today is really changing how we do astronomy. That LSST is a facility that delivers data products. That these are the data products that we're going to deliver, and that those documents that I showed you at the very beginning define them. Please take a look at them, familiarize yourself with them. Let us know, actually, if you see how they can be improved. And finally, along with the data products, the LSST will also deliver the software used to create them that you can modify and rerun yourself. And we're hoping that will spur all kinds of new data analyses. And Robert will now talk a little bit, not exactly about that software, but about the kinds of techniques and methods that are in it. So thank you all.